Hi all, welcome back, and in this video we are going to learn about partition. So in the previous video we were learning about relation, and now we are learning about partition. So of course you can relate these terms from relation to partition. So let's study partition in terms of relation, okay? And relation, we are dealing of the mathematical relation, please keep in mind, right? So okay, let's begin with this topic. So partition doesn't mean that it's we'll see what does it does means in terms of relation, but partition means that we are dividing a subset into different into its components, right? Okay, so enough of the introduction, but now let's talk about what does this partition means. So let's say we have a non-empty collection, okay? A non-empty collection. Now, collection could be of a set. You can consider a collection as a set or a relation consisting of certain elements. So we have a non-empty collection. Let's denote it by P, and it contains S1, S2, dot 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 up to Sn. So uh, it's a collection, right? Of non-empty of non-empty subset. Now it's a collection of subsets, right? Subsets of set S such that first thing is S1 union S2 union S3 union dot 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 union Sn is equal to S. So union of all these subset is equal to the set S, and if we are taking the intersection, so it is an AND condition, S1 intersection Sj, if we are taking the intersection of two set, it is equal to phi when I is not equal to j. Okay, so intersection of two set is equal to phi, and if we are taking their union, we get the original set. So this union part, this is called collectively exhaustive, collectively exhaustive, and this part is known as obviously mutually exclusive. Mutually exclusive. So if these two conditions are being followed onto this P, such that for any set, if the subset, we are taking the subset collection and the subset of each of them, if we combine them together, we get the original set. And if we are taking the intersection of two subset, two such that Si and Sj, such that I is not equal to j, then the intersection is equal to phi. That is no common elements in present in between them. If such we are getting, then it is known as a partition. Now you got what does partition means here. Now let's see some examples based on to this. Okay, so let's say we have a set consisting of elements like 1, 2, 3 and 4. Okay, now we are making some p1, like this is p1 is a partition and it contains the subset for s. So let's say the subset are 1, then we have 2, then we have 3, and then we have 4. Now for each subset, if you combine all these subset 1, subset 2, union subset 3, union subset 4, then what you are getting? You're getting 1, 2, 3, and 4. Okay, so if you are combining all the elements of the subset, then you're getting the original subset, right? If you are making an intersection of each subset, like 1 and 2, we are making the intersection, so it is equal to 5. Similarly, 2 and 3, 5, 3 and 4, 5, 1 and 4, 5, 1 and 3, 5, like 2 and 4, 5. Okay, so this both the conditions are satisfied, hence p1 is a partition. So we can say p1 is a partition on s. right? So this is all, this is about partition. Let's see some more examples on partitions. So if understanding the same set, considering the same set as base, we have another partition P2, and P2 consists of three elements, three subset, that is 1 3 and then 2 and 4. 2 and 4. Now this is also a partition. Why? Because if you take the union of all these subset, you are going to get S for union, and if you are taking intersection of any two, you are getting 5, right? So these two conditions satisfied, hence P2 is a partition on set A. So P2 is a partition on set A. Okay. Sorry, S. We have the set S, so it is partition on set S. Now let's see another partition P3, and in P3 we have elements of P3 are 1, 2, 3, 1 to 4, and then we have another subset consisting of element 3. So these are the two. Okay. Now, if you are taking the union of these two subset, then you are getting the original set. If you are taking the intersection of these two, you are getting 5. So P3 is also a partition on set S. Okay, right. Now let's say we have a P4. So we have this here P4, and P4 consists of 1, 2, 3, 4. Okay, it has only one subset. So if we are taking the for this subset, if we are taking the union, obviously we are going to get the set S, and if we are taking the intersection, we are going to take 5, because there is only one element. So no intersection of this with 5 we can take, or we can't take intersection. They are not two separate subset here. So union will give us. So this is also satisfied, but it is called one partition, one part partition. So all these are example of partition. So now I hope you would be able to get what does partition means. But there could be some other divisions of the set into its subset, which couldn't be like partitions for that set. For example, if we consider P5, and we are taking 1 2 as one subset, and 2 3 4 as another subset. Now this is not a partition. Why? Because even you do combine this into set, you are getting the set S, but intersection of these two will not equal to 5, so it is not a partition. Similarly, if we take P6, and here it is one element is 1 6, another element is 3 4, so it is also not a partition. Why? Because although the intersection of these two elements, intersection gives us 5, but the union doesn't gives us the original set, so this is not a partition, right? So this way you can find out whether it a given set is a partition of the set or not, right? Now let's see another uh, related topic with partition, that is called refinement relation. Refinement relation. Okay, now what does this refinement relation means? I guess it's not changed. Just a second. Ah, okay. So this is refinement relation. Now, what does refinement relation means? Let S be a set. So we have considered it S be a set, and for this set, we have Pi and Pj are the two partitions, are two partitions of S. Okay. So Pi and Pj are two partitions of S. Pi refines Pj. Now, what does that means? Pi refines Pj. Okay, this is very important thing to note. So Pi refines Pj means Pi is the refinement of Pj. Pi is the refinement of Pj if every part of Pi, every part of Pi is a subset of, some part of in Pj. So it seems that pj supersedes pi, right? So if we say pi refines pj, so pi is called the refinement of pj. Pi refines pj means pi is the refinement of pj, and every part of pi can be obtained from the any part from pj. Okay, so any part of pi can be obtained from any part of pj. I mean, every part of pi can be obtained from any part of pj. Now let's see what does this statement means regarding refinement. So if we have set s, and here we have 1 2 3 4, let's define two partitions on set s. So let's say p1 is a partition on set a, and it consists of element 1 2 3 and 4. Okay, now P1 is one refinement, and P2 is, let's say, another refinement consisting of 1, 2 and 3, 4. Now we will say that P1 refines P2 if P1 elements can be obtained from each of the P1 elements can be obtained from the uh, from some part of pj. So 1 can be obtained from 1 2, 2 can be obtained from 1 2, 3 can be obtained from 3 4, 4 can be obtained from 3 4, right? So we can say that p1 refines p2. But if we say that is let's say we have another set p3. Okay, and in p3 we are having 1 2 3, or 1 2 4, and here we have 3. So can we say that P2 defines P3? So you have to see every element of P2. So 1 2, can it be obtained from any element of P3? Yes, it can be obtained from this subset. So 1 2 can be obtained from 1 2 4, but 3 4, can it be obtained from any subset, any element of P3? So from 1 to 4 we can obtain 4 but not 3 4. From 3 4, this we can obtain 3 but not 3 4. So this is not possible. So we can't say that p2 defines p3, right? But does p2 but if we say if we have a p4, right, and p4 consists of one single element 1 2 3 4, so can we say that p2 defines p4? So if you see P4, P2, so 1, 2 can be obtained from 1, 2, 3, 4, and 3, 4 can be obtained from 1, 2, 3, 4. So yes, P2 defines P4. So this way you can check it out whether one partition refines another partition or not. So based on that, we can get some results like refinement relation, refinement relation that is defined as alpha on set of all partitions, on set of all partitions of S is POR. Okay, is called POR, right? So refinement relation alpha on set of all partitions, set or partitions of, it's called POR, such that if pi is a partition and pj is a partition, so pi refines pj, right? Pi refines pj is reflexive, right? And second is pi, if pi refines pj, this is the refinement relation, right? So if pi refines pj and pj refines pi, then definitely pi is equal to pj. Okay, and third is if pi refines pj and pj refines pk, right? Then it implies that pi refines pk. So this is transitivity, something called transitivity. And if pi refines pj, pj refines pi, then it is pi is equal to pj. And if pi refines pj, then it is a reflexive. So here if you see, pi refines pj, right? Where is this? So this is P1 refines P2. Okay, so it is a case of reflexive. Okay, so this is the refinement relations on partitions of set S and about POR. Now we will learn about equivalence relation. So this was one small topic that I needed to discuss, and next we will learn of equivalence relation, which is the important topic we have to discuss right now. And I hope this partition term is clear. So I just talked about this part because we are going to learn about this in the upcoming equivalence relation section. Okay, so yeah, that's all for this part, and if you do have any comment or question, please do post in the comment section. Thank you very much for watching. Thanks.